For the same thing I have, but if you which tells us.
Yeah, which is what I think. Because this is the end of the 6th week. This is the 6th week. So 18 is Friday.
Yeah, great.
Conversion evidence.
15
Days?
weeks for 60.
Yeah, it's like 45 days.
That's
Yeah, I mean,
Okay, you're live and I'm reading. There's some partial weeks.
okay, you simplify that trisection. Okay. Where did we leave off last time? I defined slice and doubly slice, and I think I gave some examples. Is that right?
Yeah.
Okay, cool. Okay, so the next thing I wanted to do is pose a question. So I had this project with Chuck Livingston a couple of years ago, where we went through the knot tables and tried to determine which knots were doubly sliced to 12 crossings. And we were sort of successful, but there were some open cases that we weren't able to figure out. So the question is any of 1173, 12A, 119, or 12A, 1202 a doubly sliced knot? So we were able to show for all but 4 knots, they were the doubly sliced. A lot was already done, but we were able to extend it to that. And then recently, showed that the Conway knot is not sliced, which was a major open problem. And so that was one of the knots we didn't know about. And so that took that one off the list. But there's still sort of these 3 knots where try as I could, I couldn't. Oh, try as I mean? Let's try to do the past tense though. What's the past tense of May? Try as I might have. Try as I might have. I wasn't able to come up with a band, two band discs, kind of like that example I worked through. We had a ribbon disc above, ribbon disc below, but you could interchange them to show that it was an knotted sphere.
Do you know if there are slices?
Yes, these are sliced. That's right. Okay. So it is known now, thanks to Lisa's result. It's known which knots up to 12 crossings are sliced. The Conway knot was the only knot that was not known. And she proved it's not sliced, and so these 3 are all sliced. Yeah, so you can, and in fact they're ribbon, which I'll define in a second. But so you have like certain bands for them.
Don't you just double the ribbon?
Well, no, so that would be knotted. That would be, yeah, exactly, Yeah, not the first one to. Okay, so if you're interested in playing around with this, this paper. The paper also has a lot of pictures of like bandings for knots that exhibit double slicing. So if you wanted to sort of play around with more things like we did last time, that'd be a good place to start. Okay. Knot K is ribbon. I can only have. There is a collection B of bands for K such that the result of resolving K along these and N component unlink, and we need to have the number of bands is N minus 1. So you attach 7 bands to K and you get an 8 component unlink. that describes a ribbon disk with 8 minima and 7 samples. Okay, so let's look at a couple of different examples. Ribbon knots. So I think we've seen this knot somewhere before. This is the stevedore knot. It's knot 6-1 in the tables, and it has a nice little ribbon disc. Yes, I think it's this. Well, maybe we should check because I'm not 100% confident now, but as these things go. So let's check what happens when we resolve this band. Well, we come around here, sort of go over and up. Whereas this guy. Like that. And so now we just need to check that that's a 2-component unlink. Since I attached one band, and there it is.
So being ribbon is equivalent to being a slice of a knotted sphere?
No, not quite. It's equivalent to being a slice of a knotted sphere in normal form.
Well, you can always put it.
You put it in normal form, and when you put it in normal form, you change the cross sections. Yeah, so being sliced is equivalent to being a cross section of a knotted sphere. A ribbon is a little bit stronger. It's a cross section where the minimum are all sort of below you. Well, that's not, there's no maximum, right?
So for slices there, and we don't the definition because I think I haven't done something with the slice image or something like that.
Yeah, slice genus. Yeah, so well, let's see. How did I define slice last time?
Like
A cross section of a sphere.
yes.
Yeah. Well, so I mean, an equivalent. Equivalent definition of slice. Yeah, so there's a couple of things. Let K be a knot, then we call it an equivalent. One is slice, which was defined to be the cross-section of a knotted sphere. Two is that K is the boundary of D, where D in B4 is a properly embedded disk. Three is that K is concordant to the unknot, okay, which means that there exists a annulus S1. There exists an annulus A S1 cross I inside S3 cross I, such that boundary of A is say K cross 1 union the unknot cross 0. And so we've got S3 cross I, and in one S3 we have our stevedore's knot, and then we have some annulus in here, and then on the other side we have just our unknot. And the only condition on this sort of surface that co-bounds these things is that that's an impulse. There's no conditions on sort of the maximum. You could define something called ribbon concordant, where you need just in general, you can define concordance between any knots K and J like this. This gives an equivalence relation on knots you can check. And if you modify that, you get an abelian group called the concordance group. And moreover, the fourth thing, or the other thing you mentioned, you could say that, it's just mostly just a rephrasing. K has slice genus or 4 genus and 0. So slice genus means you look at you're not in the boundary of B, and you look at the minimal genus surface that it bounds inside B4 properly embedded. And this is what the four-ball genus is that you mentioned, the slice genus. So slice knot is a knot of slice genus 1 because it bounds a 0. It bounds a disk genus to the surface. Okay. Very quick.
Is that like using any number of bands the not become such something?
Yeah.
So is there
If you use any number of bands, you can always. That's right. You can always get your knot to become an unlink. But you may increase if the bands are more than the number of unlinks you get at the end. Then you'll be tracing out a ribbon surface. Yeah. So yeah, one thing I wasn't going to define is what it means for like a knot to bound a ribbon surface. So similar to the slice genus, maybe you have like a ribbon genus where you ask for the minimal genus surface that the knot bounds in B4 without any maximum. So there's a whole world here that we're like dipping our toes in the water. We've seen a lot of this stuff in these seminar talks lately. People talking about this. Allison, Louise, and Maggie talking about ribbon stuff.
I think actually ribbon genus is about immersed things in S3.
Mm-hmm.
But I guess it's, yeah, you can push it into the formal.
Yeah. Okay, well, I'll segue back to this proposition based on your comment, Jason. Oh yeah, I rolled this proposition. Okay. Okay, the following are equivalent. So K is ribbon. K is the boundary of a D with D in B4, such that D can be isotoped to lie in Morse position with respect to the standard height function on the 4-ball, so let's say -30 or something, such that H restricted to D has no maxima. So this is what has come up, I think, a couple of times, which is that a knot is ribbon if it bounds a slicing disk with no maxima relative to the height function. And then lastly, K is the boundary of R, where R in S3 is a ribbon immersed disk. And what do I mean by ribbon immersed disk? I mean all self-intersections are ribbon type. And what I mean by ribbon type is you've got some piece of your immersed disk and it's intersecting itself. And the way it intersects itself is some strip of it passes through the interior of some other part of it. So you can imagine taking a literal ribbon and cutting like a small slit somewhere in its interior and threading it through. Okay. So there's There's a picture I like to draw of this. So you'll have to indulge me here. Okay. Okay, so this is something you could make on your own, right? This is this floppy multicolored disk, and what it does is it intersects itself in 3 space. But as you can see, each intersection is of the sort of prescribed form where we have a band going through the interior. And there are 2 self intersections. There's yellow one here and this blue one here. Okay, and the underlying knot, I don't know. It's super obvious. The square knot again. Okay. So one thing that's pretty easy to see is that if K is ribbon, then K is slice. For example, if you're thinking about ribbon from a ribbon immersed surface, then what you do is you take a small neighborhood of a ribbon intersection in the interior part of the disk, and you perturb it slightly into 4-dimensional space while leaving the rest in the boundary, and that removes the intersection 4-dimensionally. So you do that there, and you do that there, and we see that this gives an advantage in 4 space. But of course, the famous slice ribbon conjecture conjectures that if K is slice, then K is ribbon. And as Maggie mentioned in her talk, this is known in certain cases. It's known for knots up to 12 crossings. It's known for most 3-stranded pretzel knots. Essentially all 3-stranded pretzel knots. But in general, it's quite open. And another open question is the following. Are any 2 ribbon disks for the unknot equivalent? Where here, I guess I'm being purposefully vague for some reason. Isotopic row boundary, diffeomorphic row boundary. Maybe you're thinking about immersed ribbons. Maybe you're thinking about disks on the floor wall. In any event, this is a totally open question. Well, it's not totally open. So one motivating fact is that Charlemagne in 1985 showed that showed that if the if D has two minima, or maybe I should say this, if D has one band, which is the same as saying it's two minima, then yes. So what would a ribbon disk for an unknot with one band look like? Well, it would mean that we take our unknot and we attach a band, some crazy band, and we get an unlink. Or said differently, we take our unlink and we attach some crazy band that spans the components, and we get an unknot. And so what Charlemagne proved is that given this picture, you have this picture. The band has to be a triplet. Okay, but what remains open is the question for more than one band. So for example, if you take an unknot and you attach, say, one band here, and maybe another band, something else. And it's unknown whether or not in any case here you can arrange that the bands be standard. Now, this problem gets much more difficult from one band to two, is that when considering pictures like these, you need to consider moves called band slides and band swings, which I guess I haven't talked about, but we'll get to pretty soon.
Did last time.
Yeah, I mentioned like, when we were simplifying, when we were putting the bands in this, I mentioned you kind of slide it off or swim it. Yeah, that I did at least do that. But there, yeah. Okay. In terms of a calculus, so I haven't introduced a banded link diagram yet, even though we've been seeing examples of them. Calculus, but that's coming up shortly. So it's a pretty cool problem, whether the unknot bounds a unique ribbon disk. Pretty cool problem. Okay, so let's conclude our detour into knot concordance and slice knots and doubly slice knots and ribbon knots by going back up into dimension 4. So a 2-knot S is ribbon if S4S can be written as B4D union B4D bar for some ribbon disk D. Okay. In other words, a 2-knot is ribbon if it's the double of a ribbon disk. Okay. As we saw from our normal form considerations, every 2-knot. So the remark is that every 2-knot S can be decomposed as S4S equals B4D1 union B4D2, because we just put the 2-knot in normal form and then move bands up and down until the equator is a knot. And then we have a ribbon disk below the DI ribbon. So to be a ribbon 2-knot, you have to be something a little bit more special, which is that you have to be the double of the ribbon disk. So use the same one on top of the other. Okay, so let's some examples. So as a first example, we can take our ribbon disk for the stevedores knot, which we had a minute ago. Remember, we had this this band, which if I resolved it, which I guess I did, it gave us this picture, right? So this is a 2-component unlink, and I can draw the dual knot to the one I drew before, whose resolution gives me the stevedores knot. Okay? So that's like giving me this picture, right? With 2 minima, we attach the blue band, and our cross section becomes the stevedores knot. Well, then we can also attach this band here, which, being symmetric with the band I previously showed you for stevedores knot, you can convince yourself that that's also a ribbon band for it, and that gives a ribbon disk above. So again, our schematics are looks like this: B2, B1. So this is some knotted sphere described by 2 minima, 2 bands, and 2 maxima with stevedore knot sitting as the equation. And this is not ribbon. So, that's not a double. But maybe I should draw the double for contrast, and then we can talk about that a little bit. And while I'm drawing it, I can think about why it's not ribbon. So what would the double look like? We'd start off similarly. We'll take the same first band, which is like this. But now, if we're going to double, then we should take the same, in some sense, the same band as our next band. Now let me see if I can have clarity. Actually, this might be, yeah. So let me sort of clarify what's going on here. I'm going to write it as this. So this was sort of our original stevedores knot, right? So this is the unlink, or this is stevedores knot. Then we resolve this band to get this picture. So this was the unlink of 2 components, and we recorded the dual band. Well, if we want the double, then we should think of the blue band as sort of going down to the minima, and the green band is going up, and they should be the same band, which we could kind of draw like that. And if you think about what happens when you resolve this, you get something like this. Moreover, if we see, in general, if we see like something like this, our band going between two pieces, and then we see this other band right here, well, one way to think about this picture is like this. It's sort of like this. I know we worked hard earlier to make sure these bands didn't do this, but that's really the way the green band and the blue band interact. And if you think about flattening out, happen if you sort of flattened it out, well, it would lie exactly on the top. So they're very closely related, but it's a little bit tricky to sort of keep in mind how they're the same band, yet they're sort of working a little bit different. It's really 2 copies of the same band that have a little bit different behavior. Yeah. So for example, in this picture, this one takes the unlink to the knot, and then this one takes the knot back to the unlink. So this is ribbon, because it's the same disk above and below. This one's not ribbon.
That's the one with unsymmetric Alexander polynomial, which shows that it's not verbal.
Okay.
It's 2 minus t.
And ribbon not verbal.
Well, that's the point. But for classical knots, switching t to 1 over t will never tell you if it's not reversible, but here it does.
I see. So, how do we know this one's not good? Good question. Well, it turns out that this is equivalent to the 2-twist spin of the trefoil. And one way you could show that it's not ribbon, which we haven't really talked about yet, is we could do a fundamental group calculation. So if you're ribbon, then you're basically, because you're touching the same bands top and bottom, the bands provide some relations. You have your knot group. So you start with your knot group in the middle, and you attach a band going down, which gives you a relation in your knot group. You attach a band going up, which gives you a relation in your knot group. So if it's ribbon, the group of the disk, which you got going down, should be the same as the group of the sphere. Okay. So in this example, you can calculate that this group is not the same as the group of either of these disks, but I guess that doesn't mean that it's not double some other way.
So I know how now. I didn't realize it was the 2-twist one.
Yes, okay, so what's the proof that 2-twist one's not right?
Its Alexander polynomial is not principal, so it has deficiency less than 1.
So we should talk about Alexander polynomials in the near future. But I guess I'm making bold claims that I can't back up at this point. Okay, any questions about that? I know I threw a lot of stuff came spilling out at the same time there. Okay, maybe I'll just mention in passing that there are other equivalent formulations of what it means to be a ribbon to knot. Definitions for a ribbon to knot. You can probably guess sort of what they are. They match the ones we had for a ribbon. A ribbon 1 knot. Namely, one thing we could ask for is an immersed, instead of an immersed ribbon disc, we could ask for an immersed ribbon ball. So an immersed ribbon ball is going to have self-intersections that look something like this. You'll have an interior piece of your 3-ball, and then another piece of your 3-ball will come crashing through, not in an arc as it did with the ribbon disc, but in a disc. Okay. You can also ask that as far as the boundary of the 5-ball, you can ask that it bounds a 3-ball and the 5-ball with no maximum. Okay, good. So unfortunately, that concludes our brief foray back down to 1 knots. But yeah, some good things that I didn't think to talk about would maybe be to understand how to calculate the fundamental group of a ribbon disc exterior. Maybe I'll just mention that. Maybe I'll just mention in passing. It's not so bad. I mean, you can think about if you have your knot here. maybe I can do this on the fly, maybe I can't. Let's see. Here's our knot. Do you guys remember where we put our base? We didn't really talk about vertical presentations with knots, but
We did.
in bridge form, yeah. Did we put, let's pretend our base point is about. I think we were doing that. So the idea is, if this is our knot and we've gone around and we've labeled the arcs to get a vertical presentation, then we've labeled this one x1, and we've labeled this one x2, and we've labeled this one x3. Then what this band is doing is it's really giving us a relationship between x1 and x3, because when we resolve this band, this meridian x1 will be able to ride through the band to agree with the meridian x3, right? But one problem is that as it goes through that way, it has to pass under the x2 string. So the relation that band is that we can go around x1, and then probably we're going to go backwards around x2. Then we're going to go around x3, and then we're going to come back and we're going to do x2. So essentially, you're conjugating the meridian x1 and getting the meridian x3. I wonder if I got the signs right there. I think this was not such a good idea, but it at least gives you an idea for how ribbon bands give you extra relations inside your knot. It's also worth thinking about the fact that if you've got your knot here, and it bound the ribbon disc, then, so this band that I've sort of drawn here, it gives a relation, but what you can sort of imagine, or what you can prove, is that the group of the knot should surject onto the group of the disc. And that's precisely because there are no maxima when we go down. Okay. We have a group here, and as we move down, all we get is these pinchings corresponding to these saddles and bands, and each one gives us an extra relation. So that gives us a surjection onto the disc. In fact, and so this came up in seminar the other day, in fact, there's a special name for discs that own slice discs that have this property, and that's that they're homotopy. So on the level of homotopy, they look like they, so D and D4 is homotopy ribbon if pi 1 of S3 minus the boundary of D surjects onto pi 1 of B4 minus. So on the level of homotopy, it looks like a ribbon disc, but a priori it might not be. And so what you have is you have that slice knots have as special examples homotopy ribbon knots. So knot is homotopy ribbon if it bounds a homotopy ribbon disc. Have as a special case ribbon knots, and all of the equalities are not known. I don't know how to do that. Question mark equals sign. There's actually a fourth thing you can put in here, which I'll just say out loud, which is you can ask that the exterior, because this is totally more advanced, but you can ask that the exterior be built with only 0, 1, 4-dimensional 0, 1, and 2 handles. So B4 built with 0, 1, 2 handles as a 4-manifold. And that sits in here. Maybe we could call this geometrically homotopy ribbon. No, that's a silly thing to say. It's not clear what this should be called. Maybe strongly homotopy ribbon. It's not really a homotopy condition. Maybe we call it handle ribbon. Something like that. And these are also all not known to be the same. So we don't really understand slice disks very well. And a lot of work with people who study knot concordance put in a lot of work of sort of determining when knots are not slice or obstructing their four-ball genus or proving that they're not concordant or showing that inside this concordance group you've got lots of linearly independent elements and things like this, interesting quotients and subgroups. But not a lot of, comparatively very little time is spent just studying actual slice knots and slice knots. So from a knot concordance perspective, you mod out by slice knots. So you just sort of forget about them. But sort of studying them and asking questions like all these different things, I don't know. It's kind of a different perspective that I think is interesting. All right. Okay, let's see if we can get back on track. So the thing I want to talk about next is banded links, or maybe banded link diagrams. Okay, first we need to introduce what is going to be a very important object for us going forward. Maybe I should just pause and ask if there are any questions about all this stuff.
Maybe a simpler reason than what I said before is that has torsion in the group.
Yeah. So, okay, but, and then we know why ribbon doesn't have torsion.
Well, homotopy ribbon doesn't have torsion in each one of its concave subgroups.
For 2 knots.
Yeah.
This homotopy ribbon disk versus homotopy ribbon 2.
Yeah, but any 2 knot, which is homotopy ribbon, each one of the commutator subgroup of the knot group is torsion.
I see.
Which is not true for that group. It might just be true.
Oh, I see. Oh, I'm
torsion,
sorry. You're saying
torsion on the nose.
You're saying this 2 knot is not even homotopy.
Yeah.
Okay. I confused myself. I see. Yeah, I mean it's also fibered with not connecting with S1 process too. So yeah, maybe it was Cochrane actually who first showed this.
Yeah. Yeah, it was.
So maybe it's actually not so straightforward. Okay, we should
Well, then there's
revisit
a
that.
deficiency thing too.
Okay.
In this special case, maybe it was known already.
Okay.
Fox knew the idea was not principal.
Mm-hmm.
62 or whatever.
Okay, I should check it when it was actually known that twist spins are not really. I think it might be Cochrane.
In general, for twist spins, it was Cochrane.
Okay. Oh, I see.
That's
That's
a
a
special group.
Yeah, I understand. Okay, cool. That's good. We'll talk a lot more about two knots. Okay, anything else? All right, so a couple of minutes left. Oh, maybe I can get to this exercise. Okay, maybe not. So a C disk tangle is a pair. You guys are going to start having bridge splitting deja vu. ZD, where Z is a 4-ball, and D inside Z is a collection, is a properly embedded collection. Properly embedded collection of C disks. And a disk tangle is trivial if D can be isotoped to lie in the isotope, let's see, relative to the boundary of D, let's say. To lie in the boundary of Z. Okay. So just like a tangle is a collection of, a B tangle is a collection of B properly embedded arcs, this is a collection of C properly embedded disks, and in both cases they're trivial if they're boundary parallel. So just some examples. The first example I want to draw is, I don't want to write this. Sorry. Okay, so that's going to be one of the boundaries. Well, so one thing I can do is I can draw this. So that describes a disk. So this is K and this is B. Then we could have our disk system is going to be, you know, the disk described by K and B. And then let's add in some other components. Maybe something like this. Right, and then we can also get a bunch of disks described by these unknotted components where the Morse function on them is assumed to just be without bands. Okay, so this would be a 4-disk. So by the way, what is the boundary of D if D is trivial? What's the boundary of Z?
I think you should be called.
Yes, you can get it.
So you should
Thank you,
be
Maura.
Yeah, good. It'll be the component unlink. Or a C component, exactly. So then maybe the second example is just take your C component unlink in S3, take some collection of spanning disks for it. Actually, let's make it a little bit more interesting. So, yeah. And push these into the formal. Because I'm pushing them in, they're obviously boundary parallel, so this is a trivial 5-disk. One more definition. A membrane constituent disk D in some disk tangled D is an embedded 3-ball B inside Z with the boundary of B equal to D union D star, union along the boundary of B, where D star is contained in the boundary of Z, and the interior of B intersect the disk tangle is empty. So think of the trace of pushing this disk into a 4-ball. We have the disk in the boundary. We push it into the 4-ball. That traces out a 3-ball, and the end result is one of our constituents of our disk. And then a membrane system. Membrane system for ZD is an embedded collection of membranes for the disks, all of the disks of D. Okay, so membranes for disk tangles, just like we had membranes for tangles. And then the proposition that is going to be the exercise is to show that there are lots of, I'll probably let you go. So the exercise for next time is figure out what this proposition is supposed to be. Okay, make a list of equivalent definitions or equivalent criteria for a disk tangle. So when is a disk tangle trivial? Okay, so we have the definition, but you should be able to come up with 1, 2, 3, 4 equivalent formulations, one of which will involve membranes. Okay, any questions?
Will it involve the slide?
What?
Sliding over board or something like
No, I don't think they should involve. Oh, I don't think they should involve sliding.
that? Because in the membranes, we just slide it over.
Yeah, we talked about those membrane jumps and slides. That was more for when two membrane systems are the same. This is more, what are some criteria that give you the existence of a membrane system? Yeah, so you could maybe think back on what are the equivalent formulations for a trivial tangle. Were these examples pretty clear? Okay. All right, let's get ready. Sorry for going a little bit over. Does anyone know what to do with this thing? No.